Hello, welcome to my presentation of Basic Electronic Engineering about blast tube cooling for aircraft generators. And my name is B. Raghuram from CSE AML section C and first year. So, blast tube cooling for aircraft generators. Blast cooling has been a major factor in obtaining phenomenal outputs of modern aircraft generators. From a small weight of materials, this subject, in spite of its importance, seems to have been neglected in technical literature, and as a result, the fundamental principles do not seem to be at all well understood. Because of this lack, the subject has been often appearing to be more involved than it actually is. It is generally understood that the amount of air flowing through a given generator depends upon the pressure differential available across the generator, and it is also well understood that the amount of pressure available from blast tube depends upon the amount of air drawn by the generator. Because of this mutual independence, flight tests are today generally taken with a specific generator and a blast tube, and it seems to be generally felt that it is necessary to test each different combination of generator and blast tube. Just as Ohm's law enormously simplified the calculation of electric circuits, so can the calculation of blast cooling can be simplified by usage of similar concepts, which will be defined, explained, and used in presentation. This line of attack clarifies the fundamental principles involved, makes it necessary to run only one series of tests on any given blast tube and one series of tests on any given generator. It is not necessary to test each and every combination of generator and blast tube. This line of attack also makes it possible to write specifications which simultaneously accomplish a number of purposes. And here we have a graphical representation of pressure volume curves of a blast tube and three representative aircraft generators. As following, you can see of aircraft A, B, and C. As we have discussed earlier, this line of attack makes it possible to write specifications which simultaneously accomplish a number of purposes. The airframe builder has a definite specifications which can be used not only to design the blast tube installation but also to test it. It need not be concerned with different generator designs. The generator builder has a definite specification that permits him enough latitude to design a generator for maximum effective use of the available air. The specification clearly indicates how much pressure should be applied to generator in laboratory tests to simulate flight conditions. Pressure volume curve of a blast tube. Pressure and volume flow in a blast tube can both be measured by means of the familiar pilot tube and either a manometer or an 8-speed indicator. Three kinds of pressure can be read: static head, velocity head, and total head, which is the sum of other two. In this presentation, all pressures except atmospheric and measures in inches of water. Total pressure is measured of total energy in the airship, and total velocity head for a fixed density is a measure of the volume of air following. For purpose of illustrating, assuming a specific blast tube insulation in a plane which is flying at a constant indicated speed, airspeed, and further assume that the position of air, air cooler, flaps, or any other air dampers that might affect the flow of generator air cooling air remains fixed. Let the total pressure at the generator end be measured with end cap so that no air can flow. Know that the end can be partially uncapped so that some air can flow, and let the volume and total pressure at the end of blast tube be measured. This reading can be repeated for a number of different volumes until the tube is wide open and total pressure is then only the velocity head at exit. Pressure volume curve of a generator. Experiment and theory alike demonstrate that pressure volume curve of a generator is substantially a simple parabola. Three such curves determined experimentally are shown in the graph above. The curve for each generator shows, for example, the pressure required to force any given volume of air through it. The 3 points where the curves intersect, the pressure volume curve of blast tube shows the respective pressure and volume that will be obtained by each generator. Thus, the pressure and volume that each generator would receive from this blast tube can be determined without actually testing each generator with this blast tube. The three generators for which the curves are shown are actual aircraft generators of different design which are products used in aircraft today. None of them has an internal fan. The pressure volume curve of the blast tube necessary for purposes of illustration was esteemed since no experimental curve was available. However, the pressures shown for the three generators approximate the pressures which have been observed in flight. These curves show how unreliable it is to impress the same pressure upon different generators for comparative tests. For example, suppose 6-inch total head is impressed upon all three generators for test. The volume of air that would be received with 6-inch lead applied are compared with the volumes received under flight conditions in the above table, which shows that the test of generator A is 58 but the flight is only 61, and generator B test is 63, flight is 64, whereas generator C it's 93 of test but only 78 for flight. And also we have an pictorial representation of simple blast tube system and generator blast tube taped from an oil cooler tube, and also the different shapes of entrance for the blast tube. Alternative method for plotting pressure volume curves. In the graph, total pressure has been plotted as a function of volume. In graph, the curves of graph are replotted with total pressure as a function of velocity head rather than volume. The pressure volume curves become straight lines, which fact is an important advantage of this method plotting. But much more important is the fact that for all practical purposes, the curves of graph are independent of air density, hence independent of altitude, whereas the curves of figure are valid for only one air density. Graph could be valid for all altitudes. However, if the abscissa were understood to be indicated cubical feet per minute, but the form of graph seems to be more convenient. Another advantage of using and plotting velocity head is that when a pilot tube is used, the velocity head is quantity that is actually measured. Even if an airspeed indicator is used instead of a manometer, it is still velocity head which operates the instrument through the scales is calibrated in miles per hour. Calculation of generator pressures during flight. In the graph, the pressure head across generator A and the velocity head indicative of volume of the air supplied was determined by finding the intersection of the pressure volume curve of the blast tube with the pressure volume curve of generator, since the amount of head lost in the generator obviously has to be equal that which is available from blast tube. By using a concept of airflow resistance analogous to electrical resistance, this point of intersection can be calculated easily without plotting the curves of graph. For any generator, the ratio would be head loss in generator by velocity head at entrance is a constant substantially independent of pressure applied. The ratio Rg may be called the airflow resistance of the generator. Similarly, the amount of head loss in a blast tube is proportional to the velocity head of the air flowing through it. Airflow resistance of the blast tube may be defined as head loss in blast tube by velocity head in blast tube. Blast tube specifications. Pressure volume curves corresponding to four blast tube specifications are given in graph. Together with pressure volume curves of three representative aircraft generators, a vertical line is drawn at a velocity head corresponding to 100 cubic feet per minute. Graph illustrates specifications ANG 1 to 13, which specifies 6 inches of water. With no limit on volume, blast tube could have a pressure volume curve corresponding to either curve. Graph curve is a pressure volume curve repeated from graph of this presentation. Graph curve shows a different idea as to what the true pressure volume curve may be. Variations affecting temperature rise. The temperature rise of an aircraft generator depends mainly upon the total loss, the amount of cooling air, the effectiveness of this cooling air, that is, where it goes, and the area of bending surface it wipes. Factors affecting output characteristics. Stunned field ampere turns available compared to those required by magnetic circuits determine the base or underspeed characteristics. Types of insulation, heat transfer coefficients, shape and size of cooling ducts, and the amount of cooling air taken through the generator determines which can be dissipated and in turn the output rating. Commutating ability, generator stability, temperature rise, and mechanical construction determines the top operating speeds. Conclusion. Fundamental theories of blast tube cooling have been developed and they are explained. The problem of blast cooling is broken down into two parts, a study of blast tube installation itself and independent study of generator itself. It is shown that performance of blast tube can be experienced in terms of two factors, internal pressure Hc and flow resistance Rt and flow resistance R plus J, a quantity analogous to ohms in a DC circuit. Thank you for listening to my presentation about blast tube cooling for aircraft generators and hope you had a basic, at least a basic understanding of the blast tube, aircraft conductors, calculations, and the usage of blast tube cooling. Thank you.